This system worked. Even though it was really modest and only made images about 1 inch cubed, it certainly made pictures that could float in the air. This was an image from an OpenGL-based software library, which is standard, using just one PC rather than a bank of hundreds of PCs, that was able to project the words perspecta and actuality floating around a torus. It's green because we used a green diode laser to control this system. And at the top is a stereo pair that you could try to fuse. A second way to create a three-dimensional image does time multiplexing rather than using a mirror, rather using an interesting application of lenticulars. So in this case, which we call the image plane lenticular or vibrating lenticular, there's a projector at the left which images light onto a optical sandwich. At the beginning of the optical sandwich is a lenticular array, and then after it is a second lenticular, but which vibrates back and forth. It sort of translates in space up and down, or left and right. And it's separated by, I guess it's 1 or 2 focal lengths of the lens. And as the arrays translate with respect to each other, the beams are steered in different directions. So the light that enters your eye is what you see, and if you map backwards through the system, you could figure out what pixels to turn on when in order to create a 3D image. So the software looks like this. There's some desired scene. It's typical to use a flower pot when illustrating these. It's rendered from the point of view of many cameras, or a camera moving along a horizontal track. The columns of that data are shuffled and sort of sheared in three-dimensional space based on the calibration of the optics that are used and how the entire architecture is made. And then it's reconstructed or played back from the 3D display, as you can see here in this figure, 3D. So one eye sees one image and the other side sees the other image, and then you see a 3D scene. This is a photograph of what it looked like when we built a prototype. It's just a projector from Dell, whose electronics we had modified to drive the DMD very rapidly. It would illuminate these 2 lenticulars, one of which would vibrate using a large flexure stage. But of course this could all be shrunk down in size. In our opinion, the imagery looked really great. It was one of the first times that it caused me to involuntarily reach out and grab a 3D image, even though I knew it was just an illusion. And so here you can see some cartoon characters and a flower pot. So the next type of display is a relatively new entrant into the class of 3D displays, which one might call a multiview volumetric display. So what is the story with multiview volumetric displays? Well, for, I don't know, 30 or 40 years, people have claimed incorrectly that volumetric displays can never do occlusion. That is, people used to think that you can never have a 3D display or volumetric display whose objects would block each other. And that's just false. So it is possible to render viewer position dependent effects, of which occlusion is just one. You can also have unusual reflectance functions like iridescence or refraction. A depiction of this challenge is shown on the right. So here you see a volumetric display from the top down. It's depicting 3 objects, which are white, gray, and black, and there are several viewing positions, A, B, and C. So it would be nice if A saw the black rectangle, and B saw the white rectangle, and C saw the gray rectangle. The question is, how do you do this? Well, as a reminder, the way some volumetric 3D displays work is by projecting light onto a surface that spins. Usually that surface is diffuse. It's sort of diffuse the same in all directions. So when you illuminate it, that light from that voxel is like a point source and goes all around the room. And it creates an image like shown on the left, which is a sugar molecule. You can see the image is transparent. That's because in this type of display where the screen is uniformly diffuse, you can't control the direction of light as it leaves each voxel. But what if you were to go ahead and change the screen? If you change the screen so that it's reflective in 1 or 2 directions, then yes, you can actually program at least the horizontal or other axis sort of reflectance of light as it hits the screen. So for example, if you want to depict a straight line in a display whose screen is a shiny specular surface, or a surface which is brushed metal only in one direction, then you would do it as follows. As the screen spins, you illuminate it. You sort of trace out the lines here. So you illuminate, for example, point SA when it's at that correct time, and you illuminate point SB at the other time, and those define the endpoints of that line. So one curious thing is that although the user perceives a line stretching from point OA to point OB, in real life it's generated by a curved intersection with this rotating screen that arcs from SA to SB. This is a photograph of our example of a multi-view volumetric display. Here you can see a snowman. When it's head on, you can see its front, and when you walk around it, you can see that its arm actually blocks its body behind it. And that wraps up our discussion of a large variety of 3D displays. I think a good thing to look at now are some steps for the future. In my opinion, there are a few different enabling technologies for good autostereo display. One is spatial light modulators that could work at least 10,000 frames per second. The second would be super resolution 2D displays. The third, if you want to pursue diffractive optic holographic video technologies, until someone comes up with some more clever use of existing components, I think it would be interesting to have active display elements on the order of 2,000 modulators per millimeter. Faster GPUs, which are those graphics processing units, are the real workhorse of rendering each viewpoint for these scenes. And presumably you're going to need better interconnect technology. If you have displays or display components with so many pixels per square millimeter, you're going to need interesting interconnects to get the data out of them, or sorry, into them. Thank you very much. This was Gregg Favalora with Optics for Hire. And I added a few references if you'd like to learn more about these topics. Thanks again.